Okay, so here we are doing 4.3. This is properties of logs. Let's start with the first box, inverse properties of logs. There's two. It says let a be greater than 0 and a not equal to 1. Let me just make a brief comment about why this is. That's because if you look at log base a of anything, let's say just x for any general number. If you're looking at say log x equals y, right? What this means, remember, is that a to the power y is equal to x, right? But if a is equal to 0, then, oh, sorry, if a is equal to 1, it says a is bigger than 0 and a cannot be equal to 1, yeah? So if a is 0 or less, actually, let's look at 0 or less. 0 or less, it's looking at 0 to the y is equal to x, but in general, you can't get x from raising 0 to a power, right? Like if you have some random number, it's not going to be possible. And if it's negative, if this a is negative power, then when I raise it to a y power, what's going to happen? Should be undefined. If I remember right. Log base a to the x is equal to x. Yeah. So 0 would have no solution. And then if it's smaller than 0, then it's going to be undefined. Is that right? Negative number to the y is equal to x. Like that, something like that. Negative 1 to the what power is equal to x. Sorry, I'm just trying to think about this now. I confused myself. Oh, negative number to a power. What's the problem with that? Okay, let's look at 1 first. So if it's 1, I have a similar issue to the 0 question, because 1 to any power is just going to be 1 back again, right? So you can't get any x in general. Does that make sense? Yeah, for negative, there's also an issue. I'm trying to remember why we have an issue. Negative power to a negative number to a power. Oh, I'm sorry. Okay, I'm thinking something else. So if this, oh, okay, I see. So if you look, actually, the statement is a little bit different. Let me write down the actual statement. This is where I was getting confused. It's this a here. This is a. So the theorem says log base a of a to the x is x, right? That's because, remember the definition of log? It says that a to the x is equal to whatever this is, right? It's just a rearrangement of the exponential function. So the reason why a cannot be 0 or less is because you're looking at a to what power is equal to, if this is 0, 0, right? But there's nothing that you raise to a power that's going to give you 0. So this is actually undefined. Or let me be more specific. Log base a of 0 is undefined. Right? There's nothing no power I can raise a to that's going to give me exactly 0. I can get close to 0, with a negative exponent, big negative exponent, but not exactly 0. And similarly, I cannot get any negative number. So like log base a of -1, for example, it's also undefined. It's outside of the domain of log. Does that make sense to you guys?
Yes.
Yeah. You can see the graphic too, because remember the graph of log? It looks like something like this, right? And it grows. And it never goes past 0. It never touches 0, and it never goes to negative. So it's kind of telling you the domain is restricted from positive numbers onwards. Okay, so that's just a side comment about that. All right, so let's look now at the theorem. Theorem says two things. Well, I erased the first part of it, but the first part says, if I take a log with a base a of that same a to any number, I just get that number back. But the way to think about this is really, this is telling you that log is the inverse of this exponential function. Remember inverses, right? F inverse says f inverse of f of x is equal to just x back, right? So this log is undoing the exponential function. It's the inverse of the exponential function. Here, let me write that on the side over here. Inverse. Inverses. Remember, it's f inverse of f of x is equal to x, and also works the other way. F of f inverse of x is also equal to x, right? Those are the two properties of inverses. So this is telling you that log function is the inverse of the exponential function and vice versa, right? So the other one is a, if I raise it to the log, then I get back x. That make sense to you guys? It just follows from the definition of log. Remember the definition of log says log base a of x equal to y. That means that a to the y is equal to x. Right? So if I insert a to the x here for my y, it's telling you that a to the x equal to a to the x. You guys got this? Yeah. Okay, so let's try some questions then. So that now we know what the inverse of an exponential function is, and we know that it works both ways. The exponential is the inverse of the original function. So let's see if we can solve some questions now. Starting with number 1. Number 1 is to simplify log base 3 of 3 to the 12.5. And then number 2 is simplify 3 to the log base 3 of 7. Okay, super simple. Same base, same base. That means these guys undo each other and you just get 12.5. In general, whatever this number is, it's just going to pop out here. The log base 3 undoes the exponent with a 3 as a base. And by the way, this will work for any base. So if you did something like ln of e to the 12.5, you just get 12.5. Right? Or if I did log base 7 of 7 to the 12.5, I just get 12.5. As long as the bases match, remember ln is base e, this is base 3, then I just get this number pop out. And then what about number 2? What do you guys think this one is?
That one just be 7.
Yes, just 7, exactly. Yep. For a similar reason, right? This is undoing that base, same base, then it's just this number pop out on the inverse. You're looking at what is 3 to what is equal to 7? 3 to the 7th. 3 to the thing that gives you 7. Yeah. So this is the thing that when you raise 3 to that power, it gives you 7. So when I raise 3 to that power, it gives me 7. And that works for any base, same like before. E to the ln of 7 is equal to 7. Well, I'm doing the wrong color here. I should do blue to be consistent here. So e to the ln of 7 is equal to 7. Log base, this changed since I have 7. Let's do something else. 7 log to the 4.5. Log base 4.5 of 4.5 to the 7th. Oh, I'm sorry, I did it backwards. 4.5 raised to the log base 4.5 of 7 is equal to 7. Okay, so you guys get the inverse property? Ready to try apply it? Let's try apply it. Before we do that though, let me just kind of remind you of what we use inverses for, like how we use them when we're solving equations. Okay, so think back to me with like one of the very simplest equations that we know how to solve. Something like 2x is equal to 6. Okay, but before we solve it, let me ask you, what's the inverse of 2 times something? So if f of x is equal to 2x, what's the inverse of multiplying by 2? The thing that undoes multiplying by 2?
Divide.
Divide by 2, right? So divide by 2, or let's think of it as multiplying by a half, right? So how do I solve this thing? Well, I just apply the inverse function to both sides of this, right? So I have 2x equal to 6. To undo that, you can think of it as dividing by 6. Actually, I'm dividing by 2. I think that's actually better. So, like you said, divide by 2, right? I divide by 2. I have my function, and then I apply the inverse on the left, apply the inverse on the right. When I apply the inverse on the left, I just get x back, yeah? And then we apply the inverse on the right, I get whatever number I have. Okay, so the same principle is going to carry over for when we're doing these log functions. Let's look at number 3. We're trying to figure out the inverse of this function, f of x is equal to ln of 2x plus 5. Okay, remember to find inverse functions, first thing we do is we switch to y's, right? We change to y. So y is equal to ln of 2x plus 5. And then what do? We switch x and y, right? So we get x is equal to ln of 2y plus 5. This is okay so far? Okay, so here's where we're going to apply the thing I was just talking about. So we have this function, right? We're going to apply the inverse to get whatever's inside here. Because I want to solve for y, right? So I'm going to take e to this x power, and then e to the ln power. So on the left, what I get is I just get that e to the x back. On the right, what happens is this e is going to undo the ln part, right? And it's just going to give me 2y plus 5. So from there, I just solve for y, and then I'll be done. So to solve for y, subtract 5 from both sides. That's going to be e to the x minus 5 is equal to 2y. And then finally divide by 2. So y is equal to e to the x minus 5 over 2. And that's my inverse function here.
I have a question.
Yep.
Why does e cancel out the ln?
Oh, because ln is actually log base e in disguise.
Oh, all right. Makes sense.
Is that all over 2 or x minus 5 over 2?
Oh, the whole thing is over 2 because
Oh.
at this stage, this is 2 equal to that, right? So you divide both sides by 2. Let me write it in different color. Y is equal to e to the x minus 5 all over 2. Like that. And then just one last step. We should write it as an inverse function. So the final answer would be f inverse of x is equal to that thing we just have there, e to the x minus 5 over 2. That will be your answer. Okay, see if you guys can figure out numbers 4 and 5. Same concept. I think 4 is actually the easier one. F of x is equal to 2 to the x minus 4. All right, I'm going to start writing out the solution. So first we just change to y, and then we're going to switch x and y, right? This is how you find inverses. Remember, we just switch x and y and then solve for y, right? So what I want to do is I want to get my exponent by itself before I can apply that inverse idea. So I'm just going to add 4 to both sides. I get x plus 4 is equal to 2 to the y. And now I'm going to apply that inverse idea. So what I'm going to do is I'm going to take the log base 2 of both sides. So log base 2 of this. Let me just shift this over so I have space. And then I'm going to take log base 2 of this guy. But the whole idea here is applying the inverse function gets rid of this exponent. So I have y. I just pull down y. What's the result? I get this part just stays exactly as it is, log base 2 of x plus 4. And this part becomes just y, right? This undid that whole exponent. So that's my answer. So I write it out now as a inverse function. So f inverse of x instead of y is equal to log base 2 x plus 4. That's it.
So if it was like 3 to the y instead of 2 to the y, would that be log base 3?
Yes.
You just take whatever number that is.
Correct.
Okay.
So think about it this way, like this is the base of the exponent, right? So when I do my log, I want to pick the same base. This is the base of the log function.
So that you undo it.
Yes, exactly.
Okay.
Yeah. Okay, that's number 4. And then one more. Okay, this is number 5 now. We're looking at f of x equal to 10 to the x plus 1. Same steps, changing to y first. And then flipping x and y. X is equal to 10 to the y plus 1. It's almost the same question, yeah? I'm going to subtract 1 from both sides. It's going to give me x minus 1 is equal to 10 to the y. Let me give myself more space again. I'm going to do the same trick. Trying to undo this exponential function. So what I want to take is the log base 10. Log base 10 of x minus 1 is equal to log base 10 of 10 to the y. Or if you like, you can just write log, right? Because remember we talked about last time how log without any indication is talking about log base 10. So you could have just said log because that means the same thing. All right, but this is a matter of personal preference. I actually don't like that. I like to write the base because different authors use log to mean different things. Like sometimes they use it to mean the natural log. ln is always the natural log though. So that one I'm gonna be okay with using, but for this one, I prefer to write the base explicitly. But that's just personal preference. If you wrote it without it, then according to our book, it means log base 10, so we're okay. All right, so let's see what happens in this one. Pulls out this 10, right? It gets rid of that. So I just left with just regular y. And then the left side stays the same, log base 10 of x minus 1. So there it is, that's the answer. Let's write it as a inverse function. So it's f inverse of x is that value, log base 10 of x minus 1. And that is it, done.